I'm investigating a ridge regression model for house price prediction. The model shows a good fit on the training data. R equals 0.85. But I suspect it might be overfitting, meaning it performs poorly on new, unseen data. The mean squared error, MSE, a measure of prediction accuracy, is 100, which is somewhat high. I'm looking for ways to improve the model's performance on new data. The lower the MSE, the better the model. My model's coefficient of determination, R, is 0.85. This suggests that 85% of the variance in house prices is explained by the model. However, this high R might be misleading if the model overfits. The MSE of 100 tells me the average squared difference between predicted and actual house prices. I'm using ridge regression, a technique that helps prevent overfitting by adding a penalty to the model's complexity. I'm evaluating this model to assess its performance and generalizability. I could increase alpha, the regularization parameter. A higher alpha penalizes large coefficients, making the model simpler and less prone to overfitting. This is often a good strategy to improve generalization. Conversely, decreasing alpha would allow the model to become more complex. This could lead to worse overfitting. Adding more features can increase complexity and lead to more overfitting, even with ridge regression. This is not typically the recommended approach to improve generalization in this situation. I can employ cross-validation. This technique is excellent for evaluating model performance on unseen data. It helps me estimate how well my model generalizes and identify potential overfitting problems. This is a key method for assessing model reliability. My solution path will involve analyzing the provided metrics, R and MSE, understanding how the alpha parameter in ridge regression works, and then evaluating each proposed action, considering its impact on model complexity and generalizability. I will first examine the R and MSE values to get a sense of the model's fit to the training data and the error associated with the predictions. I see that you're worried about overfitting. That's a common problem in machine learning. It means your model is fitting the training data too well, but it's not generalizing well to new, unseen data. A high R squared, 0.85, suggests a good fit to the training data, but the mean squared error, MSE, of 100 tells us the model's predictions are off by an average of 100 squared units. We need to find ways to improve model performance on unseen data. The R-squared value of 0.85 means the model explains 85% of the variance in the house prices based on the training data. That sounds pretty good, right? However, the MSE of 100 indicates a significant error in the predictions. This discrepancy suggests a possible overfitting problem where model performs well on the training data but not so well on unseen data. Increasing alpha strengthens the penalty for large coefficients in ridge regression. This forces the model to simplify, reducing its complexity and preventing overfitting. Think of it like this: I'm adding a constraint or a penalty to avoid too complex models. Cross-validation is a powerful technique to evaluate model performance. I use it to get a more reliable estimate of how well my model will generalize to new data by testing it on multiple subsets of the training data. This helps me catch overfitting before it becomes a major issue. Decreasing alpha weakens the penalty. The model becomes more flexible and can fit the training data more closely, but this increases the risk of overfitting to the training data. This might seem counterintuitive, but think of it as letting the model be more complex, which makes it more prone to errors on new data. Adding more features can indeed improve model fit initially, but increases model complexity. More features also increase chances of overfitting because the model might start learning the noise in the data, rather than actual underlying patterns. It's better to carefully select relevant features first. The overall goal here is to evaluate how well the ridge regression model is performing. I check this evaluation using various metrics like R-squared and MSE, and use cross-validation to estimate how well the model will perform on new data. The question is asking which actions will improve the model's ability to generalize to unseen data. Generalization is the ability of a model to predict well on new, never-before-seen data points. I see a problem here. We have a model with a high R-squared, 0.85, suggesting a good fit to the training data. But we suspect it's overfitting. It performs really well on the data it's already seen, but we worry about its performance on new data, the mean squared error, MSE, of 100 tells us the average squared difference between our predictions and actual values. This is a pretty typical scenario in machine learning. This gives us some clues to work with. R squared of 0.85 means our model explains 85% of the variance in the house prices based on training data. However, an MSE of 100 tells us there's still quite a bit of error, which raises concerns about overfitting. This is about evaluating our model's performance. Specifically, it focuses on how well our ridge regression model, a technique to predict house prices using features like size and location, is performing. We want to figure out if it generalizes well to new, unseen data. I'm asking you to identify actions that would improve the model's ability to predict house prices accurately on data it has never seen before. This is all about making sure your model isn't just memorizing the training data, but actually learning patterns that apply more generally. Increasing alpha in ridge regression adds a penalty for large coefficients, which reduces the model's complexity and helps prevent overfitting. It's like adding a brake to the model to prevent it from getting too specific to training data. Decreasing alpha does the opposite. It increases the model's flexibility, which might lead to the model overfitting the training data even more. It's like removing the brakes from the model and letting it go too fast. Adding more features can sometimes make things worse, especially if those features aren't truly relevant or if they add more complexity without adding predictive power. It's like adding unnecessary ingredients to a recipe. It might actually make it taste worse. Cross-validation is a fantastic technique for assessing how well a model will generalize to new data by splitting the available data into multiple subsets and training on some and testing on others. It's like testing your recipe on different people before serving it to everyone. You'll get a more robust evaluation. I'm given a ridge regression model predicting house prices. The model's R squared, a measure of how well the model fits the data, is 0.85. And the mean squared error, MSE, average squared difference between predictions and actual values, is 100. I suspect overfitting. The model is too closely tied to the training data and won't generalize well to new data. I need to choose the actions that will likely improve the model's performance on unseen data. Increasing alpha in ridge regression adds a stronger penalty to large coefficients. This prevents the model from becoming too complex and reduces overfitting. It's a good choice here. Decreasing alpha weakens the penalty on large coefficients. This allows for more complex models, possibly increasing overfitting. This is not a good choice given my suspicion of overfitting. Adding more features might increase model complexity and overfitting, even with regularization. This likely isn't the solution. Cross-validation helps assess how well the model generalizes by testing it on different subsets of the data. This is a great way to identify overfitting issues. It's a good choice. I'm evaluating a ridge regression model. Ridge regression is a technique that adds a penalty to the model's complexity, helping to prevent overfitting. I see a problem. You're using ridge regression to predict house prices, and you suspect overfitting. Overfitting happens when your model learns the training data too well and doesn't generalize to new data. That means it performs great on the data it's already seen, but poorly on new, unseen data. The question is, how can we fix this? Here's what we know. The R-squared value of 0.85 tells me that your model explains 85% of the variance in the house prices. While it sounds good, I need to consider mean squared error, MSE. The MSE of 100 tells me, on average, my predictions are off by the square root of 110 units. That's a pretty big error. This combination suggests my model might be overfitting. Let's find out which actions will help improve how well the model works on new data, generalization. That's the whole point of this quiz, right? Increasing alpha in ridge regression adds more penalty to the model for having large coefficients, making the model simpler. Simpler models tend to overfit less. Decreasing alpha, on the other hand, would do the opposite. I would let the model become more complex, potentially increasing the risk of overfitting. Adding more features might increase complexity and cause overfitting. Think of it like trying to solve a simple puzzle with too many pieces. It can make it harder, not easier. Cross-validation is a crucial technique to evaluate a model's performance on unseen data. It helps me to avoid overfitting and provides a more reliable estimate of how well my model will generalize to new, unseen data. It's a critical step in building a robust model. This question asks you to identify actions that will improve how well the model performs on new, unseen data, its generalization ability. We're looking for strategies to reduce overfitting. Remember, overfitting means the model is too closely tied to the training data and won't perform well on new data. Increasing alpha strengthens the penalty term in ridge regression. Think of this as adding a break to the model's learning. A stronger break prevents the model from becoming overly complex and fitting the training data too tightly, hence improving generalization. Reducing alpha weakens the penalty. It's like removing the break. The model becomes more flexible, which could lead to it fitting the training data perfectly, but potentially failing on new data because of overfitting. We want to avoid this. Cross-validation is a powerful technique for evaluating model performance and preventing overfitting. We don't just train the model once. Instead, we split the data into multiple subsets. We train the model on some subsets and evaluate it on the others. This gives a more robust estimate of how the model would perform on completely new data. It's a much better way to assess generalization than just looking at how well the model fits the training data alone. We're dealing with a model that might be learning the training data too well, but not generalizing well to new data. That's overfitting. The R-squared of 0.85 suggests a good fit to the training data, but we need to check how the model handles unseen data. The R-squared of 0.85 tells us that the model explains 85% of the variance in house prices. The mean squared error, MSE, of 100 tells us on average how far off our predictions are from the actual house prices. A lower MSE is better. A high R-squared, coupled with the suspicion of overfitting, suggests the need to make the model more robust. I would increase alpha. Alpha is a parameter in ridge regression that controls the strength of the penalty applied to large coefficients. By increasing alpha, I penalize complex models, pushing the model towards simpler solutions that generalize better and are less likely to overfit. Think of it like this: a simpler model is less likely to memorize the quirks of the training data. I definitely use cross-validation. It's a technique to evaluate the model's performance on unseen data by splitting the dataset into multiple folds. Training and testing on different folds provides a more reliable estimate of how well my model generalizes to new data, helping detect overfitting. I need this to check whether my model is actually overfitting or not. I would not decrease alpha. Decreasing alpha reduces the penalty on large coefficients, which increases model complexity and increases the risk of overfitting. It's more likely to memorize the training data instead of learning general patterns. To make the model better at predicting house prices on new, unseen data, generalization, we need techniques that prevent overfitting. This question challenges me to identify actions that will improve model generalization. I would not increase the number of features blindly. More features can lead to overfitting, especially if they aren't relevant. A better approach might be to select only useful features or reduce the dimensionality of my features before adding more.